Hi, I'm Camille Beckett. I'm an undergraduate student at SUNY ESF, and today I'll be talking about our group's research on the chemistry of radical intermediate in mercury zero oxidation in the atmosphere. Methylmercury is a neurotoxin that bioaccumulates in fish, and young children are particularly at risk for developmental problems from consumption of mercury in fish. Methylmercury is formed from stable mercury 2 compounds, which mostly enter ecosystems from the atmosphere. Mercury 2 is formed in the atmosphere from oxidation of atomic mercury, mercury 0, which is emitted by gold mining and fossil fuel combustion. Modeling the oxidation and reduction of mercury in the atmosphere is important to understand where and when mercury enters the ecosystem. Current models of atmospheric mercury do not include the formation or fate of HO-HDO radical from the two-step mechanism. This mechanism is likely to be a major path for oxidation of mercury 0 to mercury 2. This radical could react in the atmosphere in a variety of ways, including abstracting hydrogen atoms from organic compounds, adding to sp2 hybridized organic compounds, or forming bonds with NO or NO2. Since there is no experimental data of any kind on HO-HDO radical, we use computational chemistry to investigate its atmospheric fate. Our results showed that HO-HDO can abstract hydrogen atoms from methane with the barrier of only 3 kilocalories per mole. It can also add to NO to form 3 conformers, probably without a barrier, therefore with very high rate constants. In addition, HO-HDO forms pre-reactive complexes with ethylene and formaldehyde, which lead to reaction barriers that are negative, so the transition states are lower than the reactants. These lead to reactions with very high rate constants. About 1 in every 10 to 100 collisions will lead to a reaction. At ground level, with concentrations typical of rural air, about 90% of HO-HDO will abstract a hydrogen atom from formaldehyde and methane. The significance of this work is that HO-HDO will rapidly form HgOH2, a thermally stable mercury 2 compound. As neither HO-HDO nor HgOH2 have been detected in the gas phase, even in the laboratory, this work shows the power of computational chemistry for investigating atmospheric chemistry. Future research should refine our results using higher levels of theory. In addition, the atmospheric fate of HgOH2 needs to be investigated.